Today we shall start with Gauss Theorem, the next application of Gauss Theorem. What is Gauss Theorem? The integral EdS, the surface integral of the electric field over a given closed surface is equal to the charge inside enclosed in the surface divided by epsilon naught, where epsilon naught is a constant. Already we learnt about a line of charge, we learnt about spherical shell of charge. Though spherical shell of charge is not there for this time in the syllabus, but it is better always to learn the concept of spherical shell. Next we move on to an infinitely large plane sheet of charge. Look here carefully. I take a large plane sheet of charge and I am placing charges. It is infinitely large, so I am placing the charges over it. Now we need to assume a Gaussian surface. What would be practically a Gaussian surface for this? Let us say the charge density is sigma coulomb per meter square, which means in 1 meter square you are going to have sigma coulomb. I will take an example model of it and show it to you. It is like this, right? A plane sheet of charge. It is infinitely large charge sheet. So I am going to assume what will be the electric field at this point P, let us say, due to the charge here. When I say there is a distance from here, equidistance, we have to go this side also. What will be the charge in that side also? So for an infinitely large sheet of charge, I am going to assume again a cylinder. Watch carefully, right? I am taking this as a Gaussian surface. Again it is a cylinder. It is infinitely large, so I am not worried about all that part. I am taking only a particular part. Okay, now this is the sheet of charge. The diagram is in 2 dimension. I am showing you in 3 dimension. Fine. So this is the charge and this is the distance it is lying. So I can assume the Gaussian surface to be a cylinder. And cylinder, it has an area of cross section. So the area of cross section is A. Now charge, this side also charge is there, the sheet is fully charged, so I extend it backward in the other part of it and there is a charge here also. Okay, the field is acting here also. This is the area vector. I hope you understand now the concept of why I am choosing the cylinder. For example, I am taking this part out now, right? And you see, this is infinitely large sheet of charge, right? And this is the infinitely large sheet of charge and I have taken this as a Gaussian surface, and the Gaussian surface in both the sides is going to be with the area A, and cylinder is the surface I have taken. Now let us take the Gauss theorem. Integral E ds is equal to Q upon epsilon naught over a given surface, closed surface. My aim is to find the electric field. So electric field into integral ds over a closed surface is equal to Q upon epsilon naught. And E into, what is the surface integral? What is the area through which the electric field is acting? The electric field is acting in this direction. Okay, electric field is acting here in this direction, right? Now the surface area, the electric field is acting over this surface area plus over this surface area. To 2 surfaces areas that are there, so I write to 2a, which is equal to Q upon epsilon naught, which is equal to. Now what is Q? The area of cross section is A I have taken. In 1 meter squared sigma coulomb is there. In A meter squared I will have A sigma coulomb charges will be there. So the charge is Q is equal to A sigma. So I substitute here A sigma upon epsilon naught. Watch carefully, the area of cross section, A is gone. So I have got E is equal to sigma upon 2 epsilon naught. So this is the formula for the electric field due to an infinitely large plane sheet of charge. Very carefully, there is only one direction. It is acting x direction. Fine. So I can take it as x cap as the vectorial quantity. So the electric field is a vector quantity which is equal to sigma upon 2 epsilon naught in x direction, x cap. So sigma is the charge density, epsilon naught is a constant. So electric field depends on sigma and epsilon naught. And the formula is sigma upon 2 epsilon naught. So we have come to the end of Gauss theorem. Gauss theorem, there are 3 applications usually we study. One is an infinitely large line of charge, right? And we took there also cylinder as an example. And we studied about spherical shell, which is not there for this year. And next, we have taken infinitely large plane sheet of charge, for which we have derived it taking a Gaussian surface, the imaginary surface, to be a cylinder and the direction in which it is acting. You may wonder, what about the electric field in this surface's sides? Because the side is perpendicular to the electric field. The side is here. Let us say this is ds, let us say, and electric field is acting. It is perpendicular. We know that EA cos theta turns to be here 90 degrees. So ultimately there is no electric field, electric flux passing through the sides, and the electric flux is only passing through the vertical area of cross section. I suppose you understand this concept, and next concept will be electric potential energy, and from where we will move forward. Thank you.